Welcome everybody to Data Modeling on Databricks Lakehouse, Myths, Truth, and Best Practices. Before we begin, forward-looking statement, we're gonna say a lot of mights, mays, wills, can, shoulds, etc. Like no guarantees. Don't plan on them, but plan on them. Okay, all right. And yeah, please complete your surveys. Feedback's really critical here at Summit. We love feedback, good, bad, the ugly, it's fine. Just go to your My Sessions or My Surveys tab in the Databricks event, find the session, give feedback to all the sessions you attend. Thank you. Cool, so intros, I'll go first. My name is Hale. I'm a lead product specialist here at Databricks, focused entirely on BI and data warehousing. Been here 3 years, been in the industry for 20, and excited to tell you today about some of the myths of data modeling on Databricks. Shannon?
Hey guys, I've actually spent 6 years at Databricks. I'm also one of our SMEs in the DBSQL side. I do a lot in our data engineering. Technically, I'm in the RCT vertical as a practice lead, and I really wish Kyle would have brought his hat today. That's a really cool one.
I won the photo battle, so that's good. So, all right. So why are we here today? So the evolving data landscape from warehouses to lakehouses, right? So I think we want to explain, like, first off, the myths, the features that you lost or you thought you lost when you went from a warehouse to a lakehouse, but actually exist on Databricks today. And also some of the best practices around just kind of modeling in general, like things that you did in warehouses that like maybe you don't have to do anymore or something like that. We just want to really dispel those myths. We hear them a lot from our customers and sometimes from our competitors. And then also just new features that recently have closed those gaps, right? So we do have, as you probably know, like we're an evolving warehouse. We just built our first warehouse product, DBSQL, released in 2020. We made a lot of progress. It's a world-class leader in TCO and performance, but there's still some features that we're continuing to add. We're not done. Nobody's done adding anything to their warehouses. We have added some recently that have kind of closed some of these gaps with legacy warehousing tools. We want to let you know about them. And then Shannon's going to kind of go into some practical considerations about the Medallion architecture and best practices for performance and optimization of your data lakehouse to assist with data modeling. So we'll do a kind of a demo, it's kind of in the can demo that Shannon will do and kind of walk through how to apply some of these best practices, and then we'll do some Q&A. Okay, so quick refresher on the lakehouse. Hopefully everybody here is super familiar with Lakehouse, but I just want to like point out one thing is like, we really pioneered this Lakehouse, which solved a lot of problems. And one of the ones is, the open data lake. And that's kind of where our, DNA started. It's like data lake solved for problems that traditional data warehouses didn't have, such as scalability and being able to kind of just like operate over big data, right? We had the 3 Vs and the 5 Vs, and at some point there were like a lot of Vs. And we used to talk about those a lot with the data lake, but data lake wasn't enough to solve these problems. So, you did have unified storage and a nice piece, but then you needed something on top. So Databricks has come up with the concept of Lakehouse. We had unified security, governance, and cataloging with Unity Catalog. And then on top of that, we've got a bunch of different compute engines, data science and AI. It's the last time you're gonna hear about AI in this talk. ETL and real-time analytics, orchestration, and of course, my favorite, data warehousing. And we've built all of these kind of with the idea that they really don't need to be siloed by compute or product. We want them unified in terms of the data, unified in terms of the experience of an analyst who goes from data ingestion and transformation to data warehousing to potentially even building machine learning models and real-time analytics on top of those as well. So we want those all to be kind of unified in one experience. And so the Lakehouse provides a lot of advantage to that. One, it can operate over lots of different kinds of data, right? It can operate at different speeds of data, real-time, streaming, and batch, all in kind of one unified interface. And then two, it can work on non-traditional kind of formats, and it can also serve up all these kind of use cases all under kind of one roof. So really, really powerful. But, there's some myths about this, and we want to kind of like address these and reconcile them. Okay, so myth number one, the Databricks doesn't support relational modeling. I actually hear this all the time. Is that, this is like a data lake, so your data needs to be like in JSON formats or unstructured formats, data is only, and when you're doing traditional tables, you're gonna need a proper data warehouse, right? And the truth of the matter is that relational principles are critical for organizing your data. That's why we called it a lake house and not just a lake. The key concept here is like, this is like organizing your data in structure actually provides meaning to business users, but also systems. And it's really, really critical. So relational modeling just didn't go away just with the Lakehouse. In fact, it's more important than ever because your data is getting bigger and better than ever. The sources are coming in, a variety are bigger than ever. You need some way of modeling this data to understand the relationships between them. That's what relational modeling does. Delta Lake supports ACID transactions, schemas, and more. So Delta Lake itself, some people think of us as, they're kind of like with CAP theorem, right? Or like a document database or a MongoDB, but we're not like that. Every table in Delta Lake is a standard table. It works atomically. It works just like ACID transactions. It works just like any traditional database table, has those same constraints around ACID for isolation and things, purposes like that. And so it works just like tables for relations as well. Then the other piece is that materialized views and metric views, our new product, they depend on relational modeling. They depend on it to incrementalize updates. So a materialized view is joining two different tables. It expects those two tables to have relations between them so it can figure out incrementally what rows it needs to update inside that overall materialized view. And the same thing for metric views, to operate over an entire model, to be able to kind of say, here's a single model that consists of relations, submit a query to it, and then have it decompile that into those joins of all those different tables, requires a good relational model. And then finally, most AI, oh, sorry, I said AI one more time. Okay, so AI models and feature tables still rely on structured tabular data. This is just true. Yeah, unstructured data is always going to be there. We do support that, we're really great with it, but structured tabular data really is the heart and soul of most of the data intelligence platform that we always talk about. And so relational modeling is a key concept there, especially when you're engineering features and trying to maintain them over time. The concepts of dimensional modeling and just slowly changing things, those still apply to things like features and the model data that sits underneath your AI tools. Okay. So myth number 2, you can't use primary and foreign keys. So for those people, some people don't know, but Databricks does have primary and foreign keys. You can set them directly in code, in SQL, and PySpark directly over your tables. And today they're informational only. So this is the truth about them, right? We don't enforce the constraints there, but you can use a rely keyword if you are managing referential integrity. So what that means is when you create a pipeline, you say this set of dimension, for example, has primary keys, this fact table has foreign keys pointing to that dimension. If you are maintaining that every row in your fact table has a corresponding row in your dimension table and has a foreign key primary key relation between it, you add this keyword, our engine takes that hint and optimizes joins between those. It converts them to inner joins. It eliminates joins when they're no longer necessary because it can understand that if there's two joins here, but this is really just the exact same set of values, it only has to look at one side of the values to figure it out. And so we can actually leverage that hint. But also enforced constraints are coming. I remember a forward-looking statement. I have no idea when, but they are working on it. It is actually going to come out sometime. I'll just say roughly, hopefully within the next like 9 to 12 months, but it is going to be probably a priority in the next couple of quarters to get started on it. Ask your friendly account team, when we have private previews, we will do enforced constraints at some point. So myth number 3, column level data quality constraints are impossible. So the truth is that you do have check and unique constraints as well. So you can have a check constraint, which specifically is like a Boolean operator that says you can't put a negative number into a quantity field, for example. Or you can't put a date below a certain range. We won't accept dates maybe below like 1900 into a date field. So that's a check constraint. You can also do unique constraints. And unique constraints are enforced. So when you do put in a row, put in a value that is into a column that has a unique constraint, and it violates that, won't let you add the row. You can go beyond this with native constraints, right? So we have Lakehouse monitoring. If you guys haven't turned on Lakehouse monitoring, you don't have to turn it on every table, but for the tables that are really critical, those are usually going to be like your fact tables or tables that are feeding into like feature tables and stuff like that. If you turn on Lakehouse monitoring, you can actually do custom expectations and data quality checks. So things like nulls, or again, values outside of a threshold, or if the average value is drifting in some direction. And you can use Lakehouse monitoring to automatically detect those, and then we put those data quality checks in the Unity Catalog Explorer so you can see them. We also send alerts when something falls out of one of those constraints. So Lakehouse monitoring is a really great way to just turn on to a tool and get a lot of what I would call the basics, the table stakes of expectations and data quality. But you can go beyond that. We have this really awesome labs library. We just released it in January called DQX. It's for custom data quality on tables as well as Spark data frames. It's really robust. You can literally write any SQL command or condition and have it apply as a data quality check. You can write PySpark as well. And seriously, give it a shot. It's free. It's in our Databricks Labs library. If you just go out there and just search for Databricks DQX, you'll find our links to it there. Give it a shot. It's a really great tool, and it's totally free. While we continue to ultimately kind of roll this into Lakehouse monitoring, so this will eventually become part of the end product. But for now, if you really need something that's just not available in Lakehouse monitoring and kind of the available metrics, you can knock your socks off with DQX. Okay, myth number 4. You can't do semantic modeling without proprietary BI tools. Okay, that was literally true about 6 months ago into private preview. Now we're in public preview with Unity Catalog metric views. So we do have our own version of semantic layer, and the cool thing is that it's tying into the catalog, right? So we have dimensions and measures. We'll have joins. You'll be able to do nested metric views, so kind of metric views on top of other metric views. So we're thinking like composable kind of metric views, especially in large enterprises. And it'll work out of the box with our AI BI dashboards, Genie, and in Databricks SQL. So, and when I said Databricks SQL, it's actually wrong. So it's like, I mean, it is Databricks SQL technically. It just works with SQL. So it's literally SQL code that you write that then in turn, like I said earlier, when you pass it to our engine, it decomposes it into the underlying joins of a regular SQL. So it's a really cool functionality. But the main thing is tying your semantic layer to a catalog. It's a major improvement over tying it to a specific BI tool because now, we're especially in the coming age of, okay, I said it again, okay, agentic AI. I won't say it anymore. But when we talk about semantic layers, we've always been talking about from a BI platform angle, but semantic layers are even more critical for AI agents who are gonna, one, generate BI for your customers, two, be assistants and genies who live next to your customers when they're doing BI by themselves and consuming it, and then also just agents just living out there like doing their own workflows and orchestrating things on your behalf. They're still gonna have to understand a semantic layer. They have to understand your logic, your business glossary, your definitions, your metrics, and these semantic layers are gonna be really critical for it. So tying it to a catalog and not to a single BI tool, pretty cool. All right, myth number 5. It's kind of a weird slide angle. Okay, yeah, you shouldn't build a dimensional model in Databricks. Okay, so we talked earlier about relational modeling, so we support this, but like some people are like, okay, but you should just build like one big table, right? Like joins are bad, and we should just flatten this all out. I get this question probably more than I should. Dimensional modeling principles are highly effective for analytics. They still there's nothing that beats them if you have a good understanding of your logical model. So if you have a good understanding of the logical model and you can build a good star and snowflake schema, those translate really well to delta tables. We love star schemas, Delta loves star schemas, Parquet loves star schemas, and our engine is actually designed for dimensional models as well. So managing slowly changing dimensions, snapshots, all those things are still true, and you still need those traditional benefits to really take to understand dimensional modeling as a value add in Databricks. We really support it. Do you always need a dimensional model? No, but you should always consider it first. You should rule it out. Okay, last one, and then I'll turn it over to Shannon. You need a separate engine for BI performance. Okay, I hear this one a lot. Okay, you guys can do really good with this ingestion and transformation. We built a silver layer and everything, and you told us about the gold layer, but we decided to serve that up in some other tool. So delta tables are based on columnar files. We just said that earlier. They're based on Parquet, right? Photon Engine is designed around OLAP queries and pruning data based on dimensional modeling. We actually do the exact same things that all your warehouses do. We just do it a lot cheaper and faster, specifically on large data sets, because pruning data is mostly a matter of like having to open files. In our world, we do a really good job of pruning files and skipping that. In other engines, they don't really have that luxury. They have to honestly spend a lot more time kind of dealing with their data pruning aspects to get those to work well, especially on very large data sets. So Photon Engine specifically designed for the cube queries and BI queries of dimensional modeling right out of the gate. And we easily scale for high concurrency workloads. So that's the other thing. We have serverless SQL. We can absolutely scale. As many users as you want to throw at it through a BI tool, we can absolutely handle it. Okay, that is it for my section of this talk. I'm going to turn it over to Shannon now. He's going to kick a few more myths and walk his demo through. Shannon?
Thanks. Thank you, Kyle. So, how many have seen this chart before? Right. So is a medallion architecture required? It's, in my opinion, it's a little bit more of a guideline, okay? It's kind of a reference point for what you want to do, okay? Let's be honest, we've all seen this chart even in traditional data warehousing. It's all doing nothing but pushing data through curation. It's everything from raw, let's clean it up, let's keep an original copy that's perhaps all the changes over time. Now I have an audit history, or if I need to go back for some sort of data quality issue that happens later and fix something, or if I have schema evolution that happens over time, I'm keeping the original copy of data. But then now maybe I want to curate it. I want to put some data quality to it. I want to put slowly changing dimensions, type 1, type 2, even type 6 or something. If you want to start doing that, you could do that at the silver layer, right? But then you have gold layer. Gold layer is a little bit more about your consumption layer. Maybe I want to now start applying optimizations. I want to cluster my data. I want to apply different things that are going to make it performant from a BI tool or from an application, ad hoc type use cases. But then what we also see is that like a lot of customers end up saying, well, I want to start doing some more curation. I want a platinum layer. I want to start doing extra things to try to make my applications work extremely well. Maybe I want to do a data vault or some other modeling layer inside of maybe my bronze and silver, and then now I want to expose that more as a snowflake layer or something like that, right? So there's usually a little bit more flexibility when it comes to how you want to build out your pipeline. It's not such a hard and fast rule that you have to follow this medallion architecture. It's just kind of a reference point in my opinion. So this one, we had 7. They told us to do 7 myths, by the way. So this is our bonus 8th, right?
Oh,
So
nice.
this one's actually, it was a true until this week, right? So we are actually announcing our multi-statement transactions this week. The multi-statement transactions are going to come in cases where, let's say your company is ingesting change data with Kafka for over 100 different Delta tables, right? And so to maintain concurrency, what you've ended up building is custom logic that uses batch IDs or views to ingest that data. It ends up being a little bit brittle, pretty expensive, but now with multi-statement transactions, you can now publish updates to all your 100 tables at once, right? So get atomicity by default and eliminate all the custom logic. Or let's say your company does supply chain planning. You need to update multiple related tables at the same time and enforce the foreign key and primary key relationships that Kyle was talking about earlier. So previously, you would have had to actually write that with a lot of different custom logic. You find and delete orphan rows, things like that. But now with multi-statement transactions that are in preview, you'll be able to update the tables with an all or none semantics. So there's a talk here at Data and AI Summit specifically around this topic. If that topic interests you, I encourage you to attend, but there's multiple ways that we actually try to improve our implementation over a traditional data warehouse. Instead of using locks, we use, optimistic concurrency, let your workloads run faster, strong isolation, support for open table formats on your own cloud storage, which ends up being fully decoupled and flexible. And there's other built in here that you see on the chart. So moving kind of from the logical data models over into more physical data models, let's talk about how we can try to keep the lakehouse optimized. So this is the part I'm actually going to have to switch over in a minute. I'm going to have to switch the screen from like an extended screen over to a shared screen on this one because it's going to be really hard to do a demo like that, right? So one of the ways to improve performance though is by reading as little data as possible, right? So when you start talking about how do I cluster data, right, to make it performant, you've built out your logical model. This is how my data gets joined together downstream from BI tools. How do I get good static pruning for those who aren't familiar with the difference between static and dynamic pruning? When you do static pruning, this is very much things like filters. It's a where clause. It's a very explicit thing you're telling it to filter by. Sometimes in BI tuning, what you want to have is, so BI tools will actually read it via join. So you need to go join to a reference table. Keeps going out. So you end up joining to a table, and then you want to have that dynamic value that comes back from filtering that other table to then go to your fact table and start pruning results. And so what happens is we'll read the dimensional, the reference tables, bring back the explicit values, push that down to the file level into the fact table to make sure that you're getting good performance. So that's the dynamic file pruning. So liquid clustering and partitioning. So liquid clustering is a little bit newer. The traditional Hive-style partitioning is actually still very valuable. I use it probably more than they like, but the liquid clustering capabilities means that you are a little bit less tethered to what your commitments are. You're a little bit less tethered to having something that's low cardinality. If you want to choose things like, I don't know, a product ID, for example, and you've got millions of products, that's a completely fine thing to cluster by now, but that would have been very problematic as a partition, right? One of the bigger challenges I see is customers who choose too many clustering columns or trying to pick the right ones. What you end up seeing is that there's a little bit more of a logarithmic increase in the amount of splits that need to happen at a certain data size as soon as you start picking too many columns. So in most cases, if you're in the low gigabytes or 100 gigabytes, 500 gigabytes even, it's probably best only to choose one column. I wouldn't start getting into the multiple columns for clustering until you get into the terabyte size because of that logarithmic increase. As soon as you start actually needing to have more files and you have cardinality, then it becomes problematic. So one of the other kind of under the hood choices you could pick is your target file size. So if you are choosing how much, let's say you've got cardinality of columns that are in the hundreds or thousands, but you want to try to pick a file size that when you load it, it actually ends up being in that magic number in that ballpark of what your cardinality is for the columns you're choosing for clustering, right? So then you can go and toggle your target file size and say, hey, you know what, I need to be as low as maybe 32 megabytes or as high as a gigabyte. For a long time, our default was a gigabyte on the target file size. And table stats. Table stats actually ends up being pretty important and very often is overlooked by customers. We're going to touch on these two here in a moment in the demo, so I'm going to jump right ahead. Okay. Just give me a moment. Okay. So what I'm going to show you here, I've already run these today, so I didn't have to actually run it live here and make a mistake, right? So what I took is a benchmark to show some data engineering, and we're going to try to do some tuning on the consumption side, figure out exactly what we want to do to try to make our queries performant. So this was the original job that I ran, and I made a copy of it. And so the reason why I made a copy of it is because then I'm starting to choose things like I want to now cluster by this, or I want to actually choose different ways to actually cluster by or optimize this table, okay? And so if I come over, I've got the first one that I did was to get a baseline, all right? So if we look at, we don't do any predictive optimization, we don't do any stats, there's no clustering involved, all right? We look at queries. These are the two types of queries you're going to see me running in here are two distinct type of queries. I'm going to run them cold, I'm going to run them warm, and then I'm also going to run a BI-like query and ad hoc type query. So the ad hoc one is like, hey, I'm just trying to pull back one row, okay? It's a user that says, I just need to go get one value. So it needs that needle in a haystack capability. I need to go pick out one individual thing, bring me back that result. I want it to be fast. The BI-like query, which is the one down here, is where I want to choose values I want to get by choosing different categories or variables that might come from a dimension or a reference table, right? So if in this case, I'm picking out, I want retail customers, I only want active companies, I want active securities, is the current version of this SCD type 2 record. So I'm kind of pulling out all these different things I might filter down from. And then down here with this trade table, I'm ensuring that the only thing I'm doing is picking out a specific year, but everything else comes from a specific join. So here I'm actually just joining to my CTE to pull back only those security IDs that came back from the CTE statement, okay? So it's very much like a BI type query. So we come back, I'm not going to show you it running right now, but if we come back, I'll pull this out. Actually, it's probably easier to do this. So here's what the baseline looks like. All right, so if you look at the SQL performance of running this with a baseline to when we actually turn on predictive optimization. So the first thing we're going to do is say, let's turn on predictive optimization. I'm not going to cluster at all. So really the only thing predictive optimization is doing at this point, since I didn't pick any clustering columns, is that it will do a couple of main things that kind of come later, which are vacuum and optimize, but those aren't going to happen as soon as I load my data, which I did this morning, right? So what it's going to give me though is stats. Remember earlier I mentioned, hey, make sure you have stats on your tables. These are the Spark open source, basically the table stats. These are different from Delta stats. So the Delta stats are actually at a file level. Table stats tells you, hey, what's the cardinality of this table? What's the minimum, maximum in the whole table for certain columns, things like that, okay? But just by having stats correct, it can build better plans, all right? And just by having stats, we actually improved our performance on warm queries, okay? 4.6 times faster for ad hoc and 2.3 times faster for BI-like, okay? So then what happens if we say, all right, I want to now do a cluster by, okay? Isn't this not working? Click over here. The left nav's not working. Okay. All right, here's no clustering, got it. All right, so here we go. This is the section we're in. So is anyone familiar with what eager clustering is? Anyone? Okay. We have some. It's kind of one of those under the hood type things too. So when you cluster a table, okay, you tell it, these are all the commands here. Here's my alter table, I want to cluster by this command, or this column. What will happen is if you are loading data into it, it will automatically cluster that data on write. So eager clustering is the same thing as cluster on write. Now you can imagine if I'm loading data over and over and over again, that cluster on write only affects that one batch that I wrote. So now that's where the optimize commands come in, is now I can actually make sure that the whole table is been able to get clustered and optimized, okay? But here all I'm gonna is just that optimized, cluster on write approach, that eager clustering, okay? So what kind of results did we get with that? Well, now we've actually taken it from 18.7 on average. These numbers are the average, by the way, so it's the cold and the warm combined. But the warm queries are the ones you're going to see the biggest uplift on. It goes from 18.7 to 11.9 when we just did the no clustering, and then now to 6.5, and that's only with the eager clustering. So one thing I always point out is like, hey, you know what? People think that keeping your data optimized is really hard or it's expensive. But if you notice on the right, I'm tracking how long this pipeline takes, right? To load this data is not free, but you can see it only went up by less than a minute by getting stats. It went up by less than a minute more, and now I have my table actually clustered, the full thing. So now I've improved my performance by up to 20 times for ad hoc queries and warm queries, and 3 times faster for BI Lake. Okay. So actually, I did have one left. Now I've got 2 left because I want to show the other one too. But all right, so let's talk about what happens if we run optimize. So this one didn't improve it that much because remember, this was just one batch. It did a cluster run right, but it does help some, right? So maybe it didn't do it the most optimal way on the original cluster because it didn't have stats on the table at all. It didn't know what the tree was supposed to look like, the KD tree under the hood for clustering. So let's just run an optimize command. And then now if you look over here, now we see results again. It did improve it a little bit, okay? You went from 6.5 to 6.3 or 8.7 to 7.7, okay? But I think this to me tells us kind of the power of the eager clustering step. It did a really good job. And then the last one I want to show you guys is I turned on, it almost didn't get ready. I don't know if the second table got ready yet. This one definitely did. So I turned on auto, right? So auto clustering, if I come up, I can show you what the commands look like. So if you see here, remember earlier I chose columns for every one of these. I said, hey, this is the column I want you to cluster by. But in production, it's a lot easier just to say, cluster by auto. You figure this out, right? Use AI. You tell me what this thing clustered by.
Oh, you said AI again.
Oh, God, is it?
supposed
We
to
should turn this into a drinking game.
Right.
So here, I turned every one of the tables into a cluster by auto, and I reloaded the data, right? Now, you have to run queries after. So what I did was made sure to run, if you look up here, the steps here is to run the queries, I think, at least 10 times. So I ran each one of the queries 10 times, and I waited about an hour. So if we come back over and take a look at, here is my schema for all this data, okay? If I come over to details, you'll see that predictive optimization is enabled, okay? You can actually change this in UI too. Right now, I don't have a warehouse on, so I can't actually start it. Okay, but if you have a warehouse started, you can choose this, and it'll actually change your predictive optimization from right here within UI. Okay. Now, if we look at dim trade, right? So earlier you heard Kyle talk about primary keys, foreign keys, the lineage, things like that, right? If you take a look, and I can zoom in here for us, you see this dim trade table? Because I have primary keys and foreign keys on this table, I have relationships out. This is the full entity relationship diagram. I can see everything it's matched to in every other table just by the pipeline being built. Okay. And if I come over to details, I'll see that I still have predictive optimization enabled. I'm choosing cluster by auto. And now what you see here is earlier where this said cluster by empty brackets, okay? But then if I come over and take a look at history, bear with me, I'm using a 2 extra small. Now, if you take a look at the history here, it took about an hour and a half. It went from 10:23 a.m. when I did that command for cluster by auto. At 12:06 is whenever the background optimization kicks in and says, we know what you want to cluster this by, right? If you take a look back, the original test I ran this morning was at 9:19 with the other, where I explicitly chose the clustering columns. This was the security ID and account ID, right? This time it chose security ID and date ID, all right? So it did choose 2 different columns. One of the columns is the same, but if you go and take a look at our script, the reason why it's a different one is if you see down here, it's actually choosing based on a year, right? So it's saying, hey, I want a year to be 2015, right? And so in this case, it said, you know what, that's just as good a value as the other column. And when I ran this query to find out what the performance was, I got 3.77, okay? And I think that I have this spreadsheet in the other sheet. Oh, wait, you know what? I have it up here. It should be down here, 2.88. So it was a little bit worse, all right? But it still chose a good column because that was actually in the explicit filter by statement, right? So here I still improved because the original queries for this one was over seconds, even warm, okay? So I just wanted to show the power of actually choosing the automated approach here too, all right? So we talked about predictive optimization, automatic liquid clustering. We've also had some advancements in our workload management tool, that tries to keep all of your queries fast as well. These are all things that work behind the scenes that you don't see as a user. But in the end, we fully support robust data modeling. We've got relational and data, dimensional modeling principles in the Lakehouse, primary keys, sparring keys, multi-statement transactions, full modeling support for data vaults, whether it's a snowflake schema, star schema, and various different ones. We also leverage Databricks features for integrity and performance. And then we've also shown how you can design some out-of-the-box capabilities to keep your jobs and your tables performant in production. Thank you.